we're going to talk about oxygen absorbers, and I have one right here. Now the question is, how do you know if an oxygen absorber is good or bad? Now, with talking with some of the manufacturers, one of the things they said is when you fill the oxygen absorber, it should feel like flour inside. If it feels gritty or like gravelly, then it's probably going to be bad. So this oxygen absorber is at 9 grams. So what we're going to do, we're going to dissect it. So we're going to take this and we're going to open this up and see what's inside. Okay, the contents of the packet weighs 8 grams, so the package itself weighed 1 gram. So what we want to do, we want to find out what exactly is in this. Now we do know that this is going to be iron powder, sodium, and activated carbon. The iron powder is actually what's going to draw the oxygen and basically rust around each iron powder particulate. The sodium acts as an activator, and the activated carbon basically maintains the reaction. So what we want to do, we want to measure how much iron powder is actually in that. And the way we're going to do that is we're going to use a magnet and a piece of paper. So we're going to cover that up, get our magnet out, and we're going to rub it around and draw up all the iron powder like that. Okay, we want to zero that. Okay, so basically in here we have 5 grams of iron powder. Each gram of iron powder will absorb 300 cc's of air. So this little packet right here was rated at a 300 cc packet. However, if you take a look down here, we got actually 4 grams of iron powder. So if you calculate that out, actually it could almost be 5 grams. So if you calculate that out, this amount of iron powder can actually absorb 1200 cc's of oxygen. And with other experiments, I have found that to be true. So the manufacturers of these little packets actually give you more bang for your buck, if you will, that they will go way beyond just the 300 cc's that they will absorb. A used oxygen absorber is not going to feel like flour, it's going to feel like gravel. So if we were to open this one up, you would see inside chunks of the iron where everything has rusted together. You can see the leftover secondary ingredients, but all the iron pieces have since rusted. There is a difference between new and used oxygen absorbers. These oxygen absorbers are used and they're coming up at 9 grams. If you get fresh oxygen absorbers, they come up weighing 8 grams.
And now for something completely different.
Okay, we're going to do a little bit of an experiment here. We're going to put an oxygen absorber into a quart jar, and I'm going to go ahead and seal this up with aluminum foil. Okay, so we're going to put this aside. This is an oxygen monitor. This will measure the percent of oxygen, carbon monoxide, and explosive gases in the environment. It is used in confined spaces. We're going to use this piece of equipment to measure the amount of oxygen and any other surprises we might have in this jar. As you can see here, there's 20.9% of oxygen in this atmosphere, and carbon monoxide is 0, explosive gases are 0. So we're going to take our jar that has the oxygen absorber inside, and we're going to pierce it and see what we find. Now, as you can see, we're down to 17% oxygen, and look at that surprise. We have 14% carbon monoxide. Why is this happening? Within the oxygen absorber are 3 ingredients. There's iron powder, sodium, and activated carbon. When oxygen comes in contact with the iron powder, there's a thermochemical reaction, basically we call rust or oxidation. When that occurs, there's a heat is generated, and everyone has felt the little packets heat up when they are exposed to the oxygen. It is that same heat that when comes in contact with the activated carbon, that some of that carbon is consumed and releases carbon monoxide. But that's not a bad thing. According to OSHA and carbon monoxide exposure in the workplace, in an 8-hour period, the maximum exposure limit for carbon monoxide is 50 parts per million. In all the experiments I've done with testing oxygen absorbers, I've never been able to get more than 50 parts per million of carbon monoxide in my testing. However, one of the things I said is a good thing is if you put an oxygen absorber in a container of food such as this, now this is oats, as the oxygen absorber removes the oxygen from within this jar, it will also produce carbon monoxide. So if there are any little critters that may be inside my oats or other grains or other food, not only will the absence of oxygen kill them off, but the added benefit of the carbon monoxide will also do the little critters in. Now, when you go to open up this jar, any carbon monoxide you're going to have inside the jar is going to quickly escape, and it's not enough to harm anybody. How long does it take for an oxygen absorber to do its job? I've reached out to many companies, some of the largest companies, and asked them, how long does it take for a 300 cc oxygen absorber to remove the oxygen out of a 1 gallon Mylar bag? And well, the first one that has come back to me has reported it takes 2 hours to fully absorb its maximum capacity. Another large company came back and said it takes 48 hours to do its work. I'm really starting to hate the term industry standard because a lot of them fall back on that phrase. And I have a feeling that they go back to the term industry standard when there really isn't an answer, or they really just don't know. Even with the 2 largest manufacturers of oxygen absorbers can't agree whether it's 2 hours or 48 hours for an oxygen absorber to do its job. Granted, there are many variables with oxygen absorbers as far as temperature and humidity. But anyway, that's what they told me. $64 question. What size is this oxygen absorber? If you take a look at it, there is absolutely nothing on here that says anything. It says do not eat. It has some Spanish thing. It's oxy-free, registered trademark. But the only reason I know that this is a 300 cc oxygen absorber, that's what I ordered. But because it's not marked, I really have no idea what size this is, and I can only trust those individuals who sold it to me that I am getting a 300 cc oxygen absorber. And that was one of my questions I asked one of the major manufacturers, and I got an interesting reply. So they said, and my question was, why aren't oxygen absorbers packs marked with the net weight, i.e. 300 cc? And their answer, and I love this one, this is an industry standard, so ours are marked the same as other in the industry, so you can compare apples and apples. Well, if that is a dumb answer, how can you compare apples to apples when you don't know what the apple is? So anyway, like I said, that's one of the things that really bothers me about everyone running back to industry standards and why these aren't marked. So I guess we just have to have faith in those individuals who sell us oxygen absorbers. I have been searching for a way to test oxygen absorbers, and like everyone else, I turned to the internet, and I found an interesting article from an Oliver Neal at Harvard University. And basically what he suggests is to take a flask such as this, and basically you can calculate the amount of cubic centimeters going up the side. And what I did is, once I found out what the true volume of the flask was, I was able to calculate at 21%, which would be the amount of oxygen, that an oxygen absorber that would be taped up here at the top, as it absorbed the oxygen, it would create a vacuum and draw the liquid up inside. And if everything went well, it should stop at the 193 cc mark. So wanting to do different shapes, different sizes, and wanting to place these in different temperature rooms, I did it with this size and with even a larger size and even a larger size than that. So I made 3 of these, all with the calculations on how much oxygen it could pull up. Now, one of the things I was concerned about doing this test is I didn't want this test to be the effect of gravity upon a liquid, because as the liquid would be pulled up into this flask, the liquid would be fighting gravitational forces to pull it back down. And so I went ahead and did these tests and came up with some interesting results. I also thought that I could also test an oxygen absorber by using a gas meter. Now this meter right here will measure the amount of oxygen in the atmosphere. This device will measure percentage of oxygen. Right now it's reading 20.9% of oxygen in this environment. It can also measure carbon monoxide and explosive gases. So what I did is I placed this device, which has a battery life of about 3 days, inside a container that I had measured the volume to calculate the amount of oxygen. And then I placed this inside with an oxygen absorber and let it run. And so basically this thing would recycle the air and would give me the reading of the oxygen as it was being depleted. This experiment did not work well because the lowest I could ever get the oxygen within the container was about 13% oxygen, and when I actually can calibrate this, I can actually get this down to 0% oxygen. And so this was not a really reliable test. I don't know if it's because of the recycled air, or whether this piece of equipment was throwing off my readings, but I will show you the results anyway. Okay, we have our oxygen tester, so we're going to go ahead and put that into the container, and we're going to add an oxygen packet. And to account for the moisture that's required, we've got a wet little paper towel that we're going to put down inside of here, and we're going to go ahead and seal this up. Okay, so we're at 20.9% oxygen and 0 carbon monoxide, so we're going to go ahead and start this. And right now it is 6:57 in the morning. We are at 24 hours into our oxygen absorber test, and we're at 600 cc's, which is 21% of the volume inside the flask. So what we're going to do to see if our oxygen absorber has maxed out, we are going to carefully open up the flask here. Let everything come out, and we're going to try to get some more air inside, and we're going to start over again to see how much more this will take up. 48 hours. On the 100 cc oxygen absorber test, this one actually has sucked up all of the liquid. So as we've done in the past, we're going to release all the liquid. Move it around, make sure we get some more oxygen inside, and we're going to see how much more this oxygen absorber will suck up. Now here's a perfect example where an experiment can go wrong. So in this case, so far I have taken up about 150 cubic centimeters of water in my oxygen absorber experiment. But there's only one problem with that. There's no oxygen absorber in the container. Basically, I believe what has happened, as the air in my house has warmed and cooled, it has created an artificial vacuum inside the flask. I'd like to address a rumor that's been going around the internet, particularly around freeze-drying websites and such. And the rumor is that oxygen absorbers cause botulism. That is so far from the truth, it's unbelievable. And it's really not being truthful for those individuals who are propagating this rumor. There is no botulism in oxygen absorbers. Botulism is a bacterium, and there is nothing inside these little packets that contains bacterium. And I think we need to kind of find out where this rumor came from. When people package their food from a freeze dryer, it's extremely important that the food is dry. Sometimes when you're taking your food out of the freeze dryer, sometimes you can move your fingers around the food, and sometimes you find little ice crystals or little pieces of ice. It is extremely important that there is no moisture whatsoever in your food prior to either putting it in jars or putting it into a Mylar bag. Got a memo here from the USU Extension Office, and one of the things they say about botulism is products that are low in moisture and oil are best for use with absorbers. Food should be below 10% moisture content for storing with absorbers. Storing food with high moisture content and reduced oxygen packaging may result in botulism poisoning. Okay, so the problem is botulism, being a bacterium, it basically gets transferred from food to food. Botulism loves to live in the earth, in the ground, where there's a little bit of moisture and either no or low oxygen. So that comes back to this little thing right here. If you have moisture in with your food because you did not dry your food long enough, whether it's in a freeze dryer or dehydrator or what kind of canning practice you may do, the oxygen absorber is going to take what oxygen is in this jar and take it either down to zero or near zero. So when you have a low oxygen atmosphere inside of here with a little bit of moisture with foods that came from the earth, now you have the perfect ingredients for botulism. But these little packets, they do not contain botulism. The oxygen absorbers can contribute to the environment to make botulism, but they do not contain botulism themselves. An email I received from the USU also basically states that vacuum sealing moist foods may lead to botulism food poisoning. Foods must be low in moisture and oil. The warning on that is botulism poisoning can occur if the moist products are stored in packaging that reduces oxygen, and they're basically saying that the moisture has to be less than 10%. So any food that you package has to be done correctly. You can contact the USU Extension Services or the FDA for tips of canning your food. But if you have botulism coming from canning, it's basically done, it's basically because directions were not followed exactly in the preparation of canned foods, but it's not from oxygen absorbers.